Welcome, or hopefully, welcome back to another episode of the Reliability Matters podcast. The challenging world of electronics becomes even more challenging when the end product is destined for harsh environments. For high reliability products operating in harsh environments, the quest for reliability is not just a goal, it's an imperative. These are not your everyday gadgets. Often they're critical components of systems designed to operate under extreme conditions where failure is not an option. From the scorching heat of desert landscapes to the unyielding cold of Arctic tundras, from the high-pressure depths of our ocean to the radiation-filled expanse of space, the demands on these electronic products are as varied as the environments themselves. While ocean depths and outer space and frozen tundras are arguably harsh environments, we don't have to look too far for examples of product failures in less harsh environments. One example that comes to mind is the current state of public EV charging stations. Government reports have concluded that up to 25% of public EV chargers are not working at any given time. While there are many reasons for this, one may conclude they are not designed and manufactured for the intended climactic operating environment. On this episode, we'll uncover the numerous challenges that designers and engineers face in their quest for reliability, durability, and functionality of the final product. As we navigate through this complex landscape, we'll highlight the strategies that enable these products not just to survive, but excel in unforgiving conditions. Our navigator for this episode is my guest, Dr. Andre Kleiner. Dr. Kleiner has 30 years of engineering, research, consulting, and managerial experience specializing in the reliability of electronic and mechanical systems designed to operate in severe environments. He received a doctorate in mechanical engineering from the University of Maryland and a master's of business administration from Ball State University. Dr. Kleiner is a global reliability engineering leader with Delphi Electronics and Safety and an adjunct professor at Purdue University. He is also a fellow of the American Society for Quality, or ASQ, a certified reliability engineer, certified quality engineer, and, if that's not enough, a Six Sigma black belt. He also holds several U.S. and foreign patents and authored multiple professional publications, including 2 books on the topics of reliability, statistics, warranty management, and life cycle cost analysis. We'll jump down that rabbit hole of designing for reliability and durability when I return in just a moment.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Andre Kleiner, Dr. Kleiner, nice to see you.
Nice to see you, and thanks for having me here on your podcast and for such a nice introduction. Yeah, it was a bit long, but thank you.
Well, that's what happens when you have a long, storied career, right? So the longer someone's been in this space, the longer the introduction gets. So I tell people we almost have to have 2 episodes. Part 1 to introduce you, part 2 to talk to you about all the stuff we introduced you about. Right, exactly.
Reliability, yes.
So let's start with this. Give me a little background on how you got into the specific space that you're in with reliability and all of that. What journey brought you there?
Well, I mean, it kind of happened because my background is actually in mechanical engineering, but I spent pretty much all my career in electronics industry, and we even joke that all electronics failures are mechanical. When you never hear of electron not making to the other side of the wire unless the wire is broken.
That's
but
a
I mean,
fair
of
point.
course,
Yeah,
it's not 100% true because we know there's some special IC based failures like latch up and hot cure injection, other things. But still, most of the things we see in the field actually kind of a mechanical nature. Still, the majority of those things.
So, I remember when I was a kid, I was always when I was a kid, we kind of were transitioning from vacuum tubes to solid state. And at the time,
I
when
remember
things
that.
went to solid state, I remember going to, my dad used to send me to Radio Shack when I was a kid to test tubes. They had a tube tester where you brought your vacuum tubes in from the TV. You weren't sure which one was not working. So he pulled out all the tubes and sent me to the store to plug them into the various sockets and test them. And I thought, at least for that brief time, I thought I was Captain Kirk. I thought I was like in control of the Starship Enterprise. That was my bridge. But when things went to solid state, the advertising at the time would say, this lasts forever because it's solid state. There are no moving parts. There are no tubes to blow or whatever. And I think I've learned over many, many decades that electronics can fail just as much as, mechanical parts can fail.
Right. And even though we don't have too many moving parts, we still do have some, but still there's a lot of mechanical nature failures in electronics. That's for sure.
And it turns out electronics are a little bit finicky. They don't like it to be too hot or too cold. They kind of like the Goldilocks where the porridge is just right. They've got a fairly wide operational range, wider than humans anyway, for the most part. But there are limits to where they like to operate reliably, which is the nature of this conversation here. So I watched an old interview. It was a 10-year-old interview of you talking about a society of engineers or something like that. And you made a statement 10 years ago where you said reliability engineers are not trained, they are grown.
Yes,
Two questions. Number one, do you still stand by that? And number two, tell me more about what you mean by they're not trained, they're grown.
Yeah, I mean, I think it's still true. One of the problems is that we don't have too many schools in this country, actually in Europe as well, which actually train reliability engineers. I was the lucky one. I got my doctorate from the University of Maryland, which actually have a program, one of the few programs in the country where you actually can get a degree and become a reliability engineer. But still, working in the industry for more than 30 years, we were not getting too many trained reliability engineers. We actually were getting maybe fresh graduates from the EE programs like electrical engineering, mechanical engineering, and we're training them to be reliability engineers. And part of my job was actually train these people, and I even created what's called a validation college, something like several training courses for newly hired reliability engineers, and as well like a basic trainings for design engineers to get them the basic principles of reliability engineers. So yes, I still stand by this statement. In fact, I'm the editor of Wiley Series in quality and reliability engineering. And I always mention that in my forwards when they say, okay, we need to basically get train more reliability engineers. And because they get a lot of the training on the job or like maybe going to conferences and taking some special courses, because like I said, there's really not too many schools in this country and in Europe where you can get a degree in this field.
Well, you just mentioned briefly about a book you co-authored. I have for those of you who are watching this podcast, I have a shot of the front of the book on the screen. For those of you who are listening in your car or on your treadmill or wherever you are, the book is entitled Practical Reliability Engineering. It's published by Wiley. It's available on Amazon and probably other sources too, but I know it's available on Amazon.
And it's on its fifth edition. And also, it's an adapted college textbook. So I know professors who use this book as a college textbook.
I wasn't going to ask you this because it probably will take us down a rabbit hole, but I'm gonna throw caution to the wind and ask you this anyway. When I was reading an excerpt from your book, it talked about how the latest edition talks about the Monte Carlo test method, and I have no idea what that is. I'm not a reliability engineer, but it did pique my interest. So maybe in 30 seconds or less, what is the Monte Carlo? I think I'm saying that right. The Monte Carlo test method.
It's not really a test method. It's Monte Carlo simulation.
Okay.
Yeah.
I picture a simulation where you're driving like an F1, Formula One car or something like that. I'm making it more exotic than it probably is.
Well, I mean, I think it's very underutilized tool in engineering. It basically, like in engineering and in some other fields, we have a lot of uncertainty. And if like even simple example, like you design something really simple and like apply the stress to certain area, and they have tolerances, for example, your side tolerances of the dimensions, and you have material properties. They also are not perfect, so you can actually model all this in perfectness or uncertainties and get the output as instead of one number, like, okay, this is my stress or this is my temperature. You can you can model it as basically a statistical distribution and say, okay, this is my mean, this is my standard deviation, this is, I don't know, my 90th percentile value if you need to have a little more confidence, things like that. And in fact, in my book, I have a whole chapter on how to do Monte Carlo simulation just using Excel, simple Excel spreadsheet, because I'm a big fan of Monte Carlo simulation.
Where did the name Monte Carlo come from? Why Monte Carlo? Why not Miami?
Monte Carlo, basically in Monaco, there's a casino.
Yes, yes.
Yeah, Monte Carlo. So it's a random, like you go and play in a casino and it's all random. It's like red.
So it could have been the Atlantic City simulation method or the Las Vegas simulation
but Monte Carlo
method.
was there before.
I agree. Yeah, good choice with Monte Carlo. So let's get a little foundation going here. The term harsh environment can be viewed quite subjectively, right? A harsh environment for one product might be a benign environment for another product. When you talk about electronics in harsh environments, how do you describe exactly what a harsh environment is and how it may negatively affect performance and reliability of the end product?
Well, you're absolutely correct. There's no kind of strict definition what is a harsh environment. But I mean, we kind of have a feeling, okay, what is harsh environment? In the industry, like I spent most of my career in the automotive, a little bit in defense industry, and this is kind of one of the examples of harsh environment. So typically we're talking about temperatures. So and not just like low temperature, like, I don't know, minus 40 degrees C or minus 40 degree F, or like a high temperature, like 80, maybe 100 degrees C or above. We're also talking about temperature cycling, which is a really key stressor in the electronics industry. And this can be quite significant. Even like with simple electronics, you turn it on and it starts heating from the inside. And in the automotive, for example, if that piece of electronics is mounted near the air ducts, and it's like in the winter, you can actually have a hottest conditions because you have this hot air going and internal heating, and we actually have seen a lot of failures during really cold months. Another factor is vibration. That's also pretty strong factor here. Besides temperature and vibration, we're also talking about humidity. And this is also a factor. And especially when you combine them all together, that's your harsh environment. And typically, as far as industries, we're talking about automotive, we're talking about aerospace, we're talking about defense industry. So, and I'm sure in some other industries, you can actually have examples. I know oil and gas, they also have their challenges. So, but again, there's no key definition. But for example, like if we're talking about a desktop computer, that probably will not be a harsh environment. So it's the temperature pretty stable. I mean, you usually don't throw it against the wall. I mean, at least most of us don't, or do something like that. But again, the electronics mounted in the vehicle, especially if it's mounted under the hood of a vehicle, that's going to be really harsh environment, and definitely needs to have some specific approaches to design, testing, validation, and other things.
Yeah, I think we've all been trained in the last 20 or 30 years on how electronics handle heat with the use of our cellular phones. If I leave this iPhone out in the sun, just maybe on an 80-degree Fahrenheit day, not extreme, really, just warm and pleasant. If I leave this out in the sun, in about 10 minutes, it'll shut off, saying it's overheating, and it'll shut itself down to protect itself. And then I have to, if I'm desperate, I'll put it in the cooler. If I'm out at the beach or wherever, or by the pool, I'll stick it in the cooler.
Come back to life.
Yeah, to bring it back to life a little faster, which may not be good in terms of cycling. It might be a little bit of a thermal shock, but it's surprising that it's something as consumer oriented as this, that's designed to fit in your back pocket and go wherever we go, has a relatively low upper operating limit, well below what humans are capable of operating in. I think another, you mentioned examples of electronics that have to work and defense and aerospace and all of that. With Internet of Things, with IoT, I'm seeing a proliferation of what IPC would call class 1 devices, which is gadget stuff, toys, things like that, things that can fail and nobody dies, going out into the field failing because they're not built necessarily to higher quality standards or higher reliability standards because they're just class 1 devices. But then again, if you buy an electronic flea collar for your dog, not expected to be high reliability, and it only lasts for 8 days because the dog is, going into harsh environments, no one dies. You have an itchy dog. Your reputation might suffer. It might result in a recall, which could be extremely costly. So I'm seeing a lot of class 1 consumer stuff because of IoT, because it's going out into the harsh, cruel world. I'm seeing a lot of applications that are having to adopt higher standards, which one might normally see in class 3 environments for class 1 products, just to get them to work, because they're not in a safe space. They're not in an Amazon server farm or on an office desk like a laptop normally would be, for example.
When you're referring to class 1 and class 3, you're talking about the IPC
yes.
kind of classifications?
Yeah. So class 1 being, consumer stuff, class 2 being maybe office products, things that need to work, but no one dies if they fail. Class 3 is, all goes bad if things fail. So class 3, defense and military, aero, all that, space, etc. So the quote unquote junky stuff that can go out, gadgety stuff that maybe is a wearable or a toy, it still has to be built to a higher quality standard than it might have had to be built to 20, 30 years ago. Part of it is miniaturization, part of it is lower tolerance for residues, things like that, and part of it is the proliferation of electronics into harsh environments.
Well, miniaturization actually may work against us because, we have smaller and smaller feature sizes, and we see more failure modes and failure mechanisms, like electromigration is becoming bigger problem at sea level than it was, 5-10 years ago. I mean, it was still a problem, but I think with this, we going to like single digits nanometers. I mean, that's pretty small. It's like
it turns out conductors like to have a little space. Like humans like to have some space around them. Conductors like to have space around them as well. And when you reduce the space, you reduce the residue tolerance, which increases the likelihood of electrochemical migration and all the manifestations of that. What are some, in a generic sense, what are some of the unique challenges faced when you're designing a product, either mechanically or electronically, to be designed and built for use in a harsh environment?
Harsh environments.
Like extreme temperatures and vibration and humidity and all that. What are some of the things that you have to consider mechanically, electronically? What are some of the things you have in your toolbox that you have to pull out at the beginning phases of design?
In my highly biased opinion, automotive is probably the most challenging. And I know, like in the aerospace and in defense, you may have harsher, like maybe higher or lower temperatures, or like stronger impacts. But in automotive, we don't have a luxury of redundancy, so we cannot put like in an airplane. You may have like two blocks next to each other, and like one fails, another one takes over. In the automotive, in most cases, we don't have this kind of luxury, so we need to design things right. And I would say, there's a lot of different aspects to designing electronics, but I would say three key things is materials, components, and interconnects. So those are the things I would say we pay probably more attention. And materials, obviously, if you deal with high temperatures, all your materials should be able to survive that. Like we used to make sensors which are installed inside the exhaust pipes. An exhaust pipe inside, the temperature can get to like 500 degrees C, easy. So, and some materials actually just melt at this temperature. But that's not the mainstream. But the mainstream would be controllers like radios in the cars. So like right now it's more complex. And so the materials, then the components, and we have the organization called AEC, Automotive Electronics Council, and actually the components we use in the automotive should meet the requirements, and those requirements are pretty harsh. So it's like about 1,000 temperature cycles, X number of hours at high temperature, a lot of tests. So they need to be qualified to be used. And in fact, like depending on where in the vehicle it's mounted, like I said before, it's in the passenger compartment. That's one kind of environment. Even in the passenger compartment, it can be pretty darn hot. And because if you park a car in Arizona somewhere, like in the sun, then things can get really hot. If you have something mounted under the hood of a vehicle, then it's a different story, because you have temperature, internal temperature. You have a temperature coming out of the engine. You have vibration coming from the road, and you also have what we call sign on random vibration. It's a vibration coming from the engine. So it's a pretty big mix of things, of environments. Is something you need to be basically cognizant of while you're designing things. And the third thing is interconnects. In as far as I remember myself, solder joints problems. Cracking was a problem. The fatigue cracking, at least in our industry, maybe it's not as bad as it used to be, but it's still a problem, especially when the industry was switching from tin lead solder to lead-free. And first, like when we started, we could not find solder which had the same fatigue properties. It basically could survive the same number of temperature cycles as tin lead, but we had to get rid of it, obviously, because of the regulations. And then we started making some progress and looking at different alloys, and finally finding things like it was what's called SAC 305. I'm sure most of you listeners are familiar with it. And actually now we have something a little bit better, which is called Inalot, which is it's a solder alloy with 6 different components going into this. So, I mean, again, that's just a kind of making a long story short. Those are 3 key things I would be looking at: materials, components, and interconnects.
And it's funny, sometimes we don't know what kind of interactions we're going to have, particularly if technology is new. And I'm thinking, going back to the early days of LED lighting, if I'm remembering the story correctly, and my guests are always good at correcting me if I'm off, but the early days of the LED electronics involved silver, like a silver backing of some sort, and the industry noticed that in certain regions of the world, these LED lights were failing, and I think one of the reasons they were failing was the propagation of tin whiskers, and
that's
further
a big one.
evidence determined that it was the sulfur in the air in certain regions of the country, and I'm thinking India, in this particular case study, had alarmingly high level of sulfur in the air, and that reacted with the silver and grew things and caused a failure. Now, that sulfur in the air, for most applications, is not in itself a harsh environment, but the mixture of silver and sulfur it was a tremendously harsh environment. And of course, the industry learned and said, okay, we're not going to do that anymore, and changed the materials. But it's kind of to my earlier point, is what's a harsh environment for product A may be a benign environment for product B. And one needs to know the limitations of every material, of every torque setting, mechanically speaking. They may have to stress relieve, wire harnesses a little bit more, to account for movement and creating metal fatigue and things like that. You kind of have to have a crystal ball and see into the future and look at interactions of interactions, right? I mean, you really have to. I think maybe that's one of the reasons you say reliability engineers are grown, because it does seem to have a pretty substantial tribal element to it. We learn off what we learn.
Yeah, it's another joke. We say we don't have Ohm's law in reliability, so I wish we had like a certain equation. We put things in and get the answer.
Never fails you. Yes, exactly.
But unfortunately, again, there's a big element of uncertainty, and you mentioned crystal ball, because part of the job of reliability engineer is actually do reliability prediction, and it's like Yogi Berra said, predictions are tough, especially about the future. So, and the different methods. I mean, I personally think that the best method is if you have field data from maybe earlier versions of this product, but in some cases we use new technology, new materials, something new, and we can do a kind of relatively decent job of reliability prediction, but it's just not going to guarantee that that's what you're going to see in the field, again, because the systems are pretty complex. And one of the things is, like, we have in the mass production industry, we have different units basically used differently, and that's what we call user severity. So, like, you drive X number of miles per day, I drive another number of miles, and someone may be driving once a week, and someone may be Uber driver in rural area and see a lot of miles in harsh, those rough roads. So you always have this distribution, and going back to Monte Carlo simulation. So you can look at this distribution of how harshly your product is used, and you need to make a decision. Okay, who am I designing my product for? So it can be like, okay, I'm going to design it for an average user, but that's probably not good enough, because that means other half is basically you don't know what's going to happen to their products. Probably it's going to fail. But on the other end of this, you cannot design for like a worst case ever happened, like the worst temperature, which we recorded like in the past 200 years. I mean, you can design for that, but it's going to be over-designed. It's going to be super expensive. So like in the automotive industry, again, we look at certain percentile of a user, and that you need to have a lot of data. I mean, with mileage, it's pretty easy because we have all this
right.
Dealership data, and we know all the mileage distributions. But what about the temperature? So, like, yes, someone is driving a car in Arizona, and someone in North Dakota, and someone in Norway. So it takes some work to collect all this data, and the same goes for other stress environments like vibration or mechanical shock or humidity. So again, you cannot design for the absolute worst case ever happen, because again, it's not going to be cost effective. So you need to stay somewhere like in the 95th to maybe 98th percentile user. And this way, we know, like, we have this Uber driver or pizza delivery guy in rural area, and he probably not gonna may have some issues with his or her car, but that's something, it's a reality of life.
Yeah, I know in the civil engineering world, I think they design for 100-year events. You know, I hear, you know, irrigation channels or flood mitigation channels are designed for the 100-year flood. Buildings are designed for the 100-year earthquake, and you know, not the earthquake that happened in 1512, right? You know, the once in a million year events. As you said, it's a question of satisfying the majority of consumers at the most efficient cost, and we could design for the one in a million year event, or one in the billion person customer that drives a car 937,000 miles a year, but everyone would pay that price. So when we talk about design strategies, I'm glad you brought up that theme, because that's my next question. What specific design strategies do you employ to enhance the durability and performance of circuit assemblies and the associated mechanical hardware that would be employed in adverse conditions?
Well, I'm not sure we're talking about strategies. Again, like those triad I mentioned before, like components, materials, and interconnects. But one of the key things is to understand your environments. And it's not always an easy thing. It's like, I'll give you an example. When we start building electric vehicles, there were a lot of questions because we kind of used to this, and I'm going to stick to my favorite topic of temperature cycling. So we kind of used to this kind of two full cycles, cold cycles per day, where like the temperature goes extreme, like, I don't know, minus 40 degrees C to plus 80 degrees C in the extreme case, but there's only two of them per day. I know that some people may have more, but those are not going to be extreme cases. But now we're switching to electric vehicle, and you have this cycle where you kind of stop and go, where things shut off, and being turned on again. And now you suddenly have, instead of 2 cycles per day, you have many, many, many cycles per day, but they are more like a lower delta T type of temperature cycles. So, and you need to kind of understand that what kind of damage they're going to do to the materials and interconnects. Again, solder joints is always a focal point. In kind of design, knowing what kind of environment, what kind of stress you're going to have, and what kind of operating profile you're going to see in the field. And like I said, sometimes it's not a very easy data to have. And to me, this is the key. You need to know your environment.
Yeah, absolutely. Speaking of knowing your environment, let's talk about kind of the elephant in the room for a lot of people, particularly if they drive electric vehicles, and that is the current state of the public charging stations. Now, I say public charging stations to differentiate Tesla branded charging stations from everything else. I don't think we can throw Tesla into the same category of public stations because Tesla seems to get that end right. But
take a little bit better care of their stations.
I think it's probably better design or better understanding of the environment in which these chargers are going to go. Recent reports have indicated that about 25% of public EV charging stations are broken at any given time. Only 75% are up for a variety of reasons. And the Infrastructure Act or the CHIPS Act, I think it came under the Infrastructure Act, is providing more than $1 billion of public funding of your money, Andre, and my money, Mike, to build out the EV public charging station infrastructure, with the caveat that if you're going to use government money, you have to make it better than 75% reliable. I think the standard I read, and I may be off a little bit, it was either 91 to 97%. And for the next decade, people will argue about how to interpret that instruction, what counts as a defect, what doesn't count as a defect, et cetera. But clearly, the goal is to make it more reliable than it is today. Based on your experience, can you provide a hypothesis on what you view could be the reasons behind the 25% failure rate on these types of devices? And what would based on your experience, what would you guess? Armchair quarterback that. What do you think that industry could be doing wrong?
Yeah, I was gonna do a disclaimer because I have a lot of experience with electric vehicles, but my experience actually comes from the vehicle side, not from the charging station side. But I would guess.
But you don't have one without the other, right? I mean, that's the
correct.
real problem with EVs right now. The number one consumer concern for EVs, number one by far, it's not close, isn't will my battery explode in my garage? It isn't the reliability of the car itself. What it is the reliability and availability of charging stations. That is the number one concern. If there's anything holding people back from adopting EVs, it is the availability or lack thereof of charging stations. A, there's not enough of them. Okay, well that will scale out over time. But B, where there are enough of them, 25% of them are broken.
A lot of them don't work.
Right.
I can just make a guess here. I think part of it, because again, I'm just guessing here, because they probably require maintenance. I don't know what's their mission life. Like in the vehicle, our mission life is usually about 15 years. I mean, there's some exceptions, but that's becoming pretty much a standard. So whatever electronics we make need to survive and be tested and validated for what's the equivalent life of 15 years. With charging stations, like I said, I don't know what's their kind of reliability and what's the maintenance plan, because it might also be some misuse or abuse, because sometimes maybe somebody just start driving away with this thing plugged in or something like that. Because typically, I used to work a lot with warranty data, and before giving you kind of educated answer, I would definitely like to look at the records, because I'm sure there's got to be some records, because somebody maintains those charging stations, and see what actually happens. I mean, how long they've been in the field, what kind of failures, at least some description of failure mode, not just this damn thing doesn't work. That's not good enough. It's like, okay, what exactly, I mean, kind of look inside and see what's happened. I mean, something broken inside, or there's got to be reasons, because to me, it seemed like the charging stations are not that complicated devices. I mean, compared to some of the electronic systems we install in cars, I mean, these seem to be more simple. Yeah. But at the same time, we know one of the key concerns when we were switching to electric vehicles was the temperature, because, obviously you go from 12-volt battery to 400-volt battery, like an 800-volt battery, and it's totally different heat dissipation. So now we had to use air cooling, and in many cases we had to use liquid cooling for those systems, because it just were no other way to take the heat out. And again, knowing little about charging station, I would say this might be a concern. Maybe they kind of overheat in some states. Again, like thinking of Arizona, and like in California, you also have a lot of sunshine, so that might be a problem. But again, without looking at some kind of record or some kind of data, I would be just giving you my guesses.
Yeah, my guess would be less educated than yours, but my guess would be the reason they're failing is a multiple set of reasons. One is they're not designed for harsh environments. The other is they didn't factor in the human factor that we tend to damage things.
Someone drives over them.
Either intentionally or unintentionally. And they didn't design in the fact that these things would be outside, not so much harsh environment. Harsh environment was definitely part of it, but just the fact that creatures and vegetation like to grow in, they can easily penetrate these boxes. I think
could very well be a problem.
Yeah, and I think that the main reason on the top of that excuse pyramid is the fact that they just did not think or care to build these things for the intended climactic operating environment. I have a feeling, and I can't base this on firsthand knowledge, but based on anecdotally anyway, I think that companies said, well, we can build this, and they didn't really understand the nature of what they were building. They didn't understand the importance of proper enclosures. They didn't understand the limitations of electronics in hot
that takes us back to just
or humid environments.
It takes us back to that discussion about knowing your environment. And like I said, to me as a reliability engineer, it's a key. And one of the projects I did, like consulting projects I did for a company, they were actually making credit card readers and used to sell them to grocery stores and other places. And they decided to start selling them to taxi drivers, to taxi fleet.
Different
and that's a
environment.
different story. Yeah, different environment, totally. So it's going to see in the vehicle basically something totally different than it's going to see at the grocery store. So I was helping this company to basically put together a test plan and to verify if their design is good enough. And my guess was from the beginning that wasn't good enough because it just was not originally designed for this kind of environment. So they needed to make some adjustments, make some changes to be able to actually use those credit card readers in a taxi fleet.
Yeah. Well, I think the reason EV chargers are failing is your fault, Andre, is because you were not involved in the reliability design. If you had been involved in the reliability at the beginning of that, if they hired you to be the master reliability engineer for EV charging stations, I would not have something to talk about right now. So,
well, if we could grow more reliability engineers,
if we could grow more, exactly. If we could fertilize that soil. Sometimes, when we think about harsh environments, we think about weather, temperature, vibration,
right?
Poster child reasons. But let's talk about the human factor. Humans tend to break things. Humans are careless. Some humans are intentionally, want to commit vandalism, things like that. In your experience, have you had to factor in what I like to call stupid human tricks? The ability for humans to do things that are unpredictable. We know that there are certain things that are predictable. Ohm's law is predictable. There are certain physics that universal laws that can't be broken. I think humans break all those laws because we are predictably unpredictable. So what kind of efforts have you had to make, or have you wished you had made, to account for the harsh human rather than just the harsh environment? Does that make sense?
Yeah, there's actually a whole section in reliability engineering which is called human reliability. I mean, it deals mostly with maintenance and assembly. Like, I'll give you an example. There's a test in many industries. There's a drop test. So, I mean, someone on the assembly line can drop things and they pick them up and put them back together, and suddenly you have a walking wounded. So in many industries, it's basically the test where if you drop it and you have physical damage, like, I mean, cracked glass or just damaged case or something, then actually you pass the test, because someone picks it up and see it's broken, and hopefully you're not going to put it back on the assembly line. But if you drop the thing and actually it doesn't function, but there's no visual damage, then actually that's considered that you failed the test, even though, like, there's no visual damage. And you pass it when it doesn't work, but there is a visual damage. But I can give you a more interesting example, because we used to make those. We still actually make CD players for cars, even though it's not as common. Now you have this USB port, but there's still cars with CD players. So when we were switching from cassette players to CD players, first we were getting things back from the field and finding like gum wrappers and coins inside those CD players. So like some kids kind of playing and sticking things in. So we have to take this into account and make this basically receptacle for a CD. So you can't really put anything in there. It's like put some kind of a door or some kind of mechanism preventing it from it. But I mean, in some cases, in severe abuse, I'm not really sure what you can do if someone just decide to throw this, make a laptop and somebody decide to throw it against the wall.
That's the billion-year storm. I mean, that would be designing for the very unusual. No one's going to be willing to pay the price universally to buy a laptop that can be thrown against a wall, right?
Yeah. But some things, you need to anticipate and kind of take care of this, what we call misuse, abuse kind of mode of operation.
Right. Let's talk about testing and validation. Obviously, there are certain tricks you have up your sleeve. Monte Carlo was one of them. Can you walk me through the various testing processes you use to validate the reliability of either circuit assemblies or the adjoining hardware
the whole module
under harsh environment conditions? What do you use in the reliability world to test out your theories and maybe simulate lifespan or something?
Well, in this point, I should ask you, how long is your podcast?
4 days, Andre. 4 days. No.
Okay, I'll try to keep it short.
Okay.
When I was teaching this to students, I was showing them a typical diagram of test flow during validation, and this diagram had like many legs, and one would just another one would have humidity testing and mechanical vibration and salt exposure, like a salt spray. And I would ask them a question. I mean, why do we need so many tests? And why don't we just stick to one test and kind of get done with it? And the answer is obvious, because different stress environments are causing different failure modes and different failure mechanisms. So you need to address all of them. So in basically, yes, a typical automotive electronics test flow at the validation phase, where basically you need to make sure that everything is working right, has all those tests. I mean, it would have mechanical tests. It would like temperature cycling. Temperature cycling is the must. I mean, you just like, you cannot not have it in the flow. I mean, you can argue about, gravel bombardment, things like that, but temperature cycling, low temperature exposure, high temperature exposure, you have vibration and mechanical shock. Like if, let's say, you mount your units in the door. And the doors, car doors have electronics in them. So you have a door slam thing. So there's a lot of tests. The only thing is, like, different car companies, they have different philosophies. Some prefer parallel tests. It's like, there's one leg, you have, 10 units going through temperature cycling, and there's another leg have 6 units going through vibration, and another unit's going through, like salt fog or like water penetration test. It's a quicker test because you do it simultaneously, but obviously in this case, in real world, you have basically simultaneous exposure. You have a combined environment, and so you're not going to have the effect of combined environment. So you're kind of assuming that's this stress is kind of orthogonal, meaning they don't affect each other, which is not true. But you have a quicker test. There's another philosophy where you do it sequentially, or some environments you can actually combine, like you can have a vibration shaker in the chamber. But again, the vibration is much quicker test, so you cannot vibrate during like 1,000 thermocycles. It's just going to be too long of a test for vibration side. So this is a trade-off, and that's basically, like I said, in reliability engineering, a lot of things are trade-off here. So you do it quicker because the development cycle is getting shorter and shorter, or you do it sequentially, or kind of where you can in parallel, simultaneously, and then you can have this combined environment effect. But
does all that fall under HALT testing, highly accelerated life testing? Is that all part of a HALT testing protocol?
Not exactly. HALT testing is a little bit different animal because we don't use HALT testing for validation, because validation is basically when you have a system in working order, everything is together. And in fact, in the automotive, we have DV and PV. DV stands for design validation, when you have a prototype, basically, but fully working prototype, and process validation when you have a production intent unit. So, but HALT is sort of a kind of test where you find the weak links of a design. So it's a pretty short test. It's a really harsh environment. Like you have a pretty hard vibration with temperature cycling, with pretty fast transition from low to high temperature. And the goal is to basically find. You cannot pass HALT test. You need to fail it. You fail the test, you find the problem, and you fix it. But HALT test has some challenges because you may fail something, but now you need to understand if this is actually kind of failure mode you're going to see in the field. In some cases it is, but in some cases it is not. It's like you crank up the temperature and something melts. Well, you're not going to see 200 C in the field, but here you have a failure. This is something we call foolish failures, but that's a reality. So yeah, HALT is an important tool in design and development, but it's not a validation. It's not a product validation tool. So
interesting. You talked earlier about one example of an innovative technology, and that was this newer solder alloy beyond SAC 305. Are there any other emerging technologies or materials that you believe will significantly impact the design and construction of circuit assemblies or the final product in general for harsh environments in the near future? Anything that you're aware of?
Well, I think it's more of an evolutionary development. But one thing I would say, prognostics, PHM, prognostics and health management, this is not exactly new technology, but this is kind of new approach where you actually monitor things and you can understand or predict this based on the models and based on the data you're collecting. The what's called RUL, remaining useful life. So if you like, very simple example, your brakes in your car start squeaking. That's actually kind of a very simple form of prognostics and health management. So they still operate perfectly, maybe not perfectly, but fine. But at the same time, they give you a signal saying, okay, maybe you need to kind of think about replacing brakes or some part of the brakes. So, and this is something people work on at the different levels. I mean, there's a lot of success stories with prognostics and health management with mechanical systems. Like, I mean, one of the examples is, I know the project where they were putting sensors on helicopter blades, and the helicopter blades tend to crack. I mean, develop like micro cracks, which will eventually develop in something bigger. So, but the vibration pattern in the profile is changing. So they start detecting that, and maybe it's time to fix or replace the helicopter blades. And there's a lot of success stories with electronics. It's still a developing field, because I was actually doing one of the projects myself where we were collecting data from one of the engine controllers, trying to basically anticipate when, I mean, we're going to have I don't know, solder joint failure or any kind of other failures. We had some success, but the problem sometimes is that you need to have this what's called path to failure, a basically degradation pattern. Like with helicopter blades, you have small cracks and then they become bigger, then become bigger. In electronics, it's not always like that. You may have a solder joint with a crack and it still functions fine. And at some point when this crack achieves a certain percentage of the area, and then suddenly, boom, you have no connection there. So it's still a developing field.
It's
but
all or nothing, yeah.
I'm a big believer.
Not linear in that case. That failure mechanism is not linear. It's sudden.
Well, we don't need linearity. It can be nonlinear as long as there's a path.
But it's not gradual.
But when it's binary,
yes, that's a better description. Yes,
yeah,
yes.
And it's a little more difficult to predict.
Yeah, we're starting to run out of time, so let me just throw a couple more questions in. Based on your experience, well, let me back up a little bit. I would assume, I don't know what it's like to be a reliability engineer, but I would assume sometimes you're the buzzkill at a party, right? You're the guy that kind of goes, no, we can't.
Nobody sits with you in the cafeteria.
Right. No one's sitting at your table. Right. Yeah. Andre's all by himself. What are some of the considerations that are either often ignored or the misunderstandings when it comes to designing products for reliability, particularly in harsh environments?
Yeah, one of the things, and that's like when you say buzzkill, one of the problems is that the mission life is much longer than the test time. So we use accelerated testing. So it's like, hey, if the vibration is, I don't know, 0.8 GRMS in the field, then we would vibrate it at like 3 or 4 GRMS. So we would compress the time. And same goes for basically any test. With operating temperature 60, so we crank it up to 100 or 110 or whatever. Electronics engineers tell us, like, yeah, this is the max you can use with this particular chips. So there's always a question of correlation between the field and the test. So when we fail something in the test, then some design engineer may start asking questions. I mean, how realistic your test? Maybe you accelerated it too much. And in some cases it happens. I can give you an example, again, going back to the CD players. I don't know why I love CD players so much. But again, when we start installing them in cars, and basically the vibration level of the road was okay, but the vibration level of our shakers, because it was much higher, because this is an accelerated test, was too much, and they would be skipping and doing some weird things. So we kind of looked at this and said, yes, technology cannot basically sustain this accelerated level of vibration. So we reduced the level, but at the same time, we needed to extend the test time, because there's always this trade-off. Okay, the higher the stress, the shorter the time because we use those acceleration models.
Yeah, interesting. And finally, Andre, our industry, like so many industries, are seeing a kind of a changing of the guard. There's the silver tsunami effect, which we've talked about on this show before, which is the great retirement, right? This is the greatest generation when it comes to the number of us retiring right now. Our history has not seen the level of people exiting the workforce through retirement in the numbers that we see it today compared to any time in our history. This is the baby boomer, the largest generation, all coming of age at the same time and all retiring. And that has opened the door for young people to come in. And for a while, we were seeing more people go out than people come in. And it was a little concerning for a while. Now I'm starting to see, I go to conferences a lot, and I'm starting to see younger people attend the conferences. I'm starting to see younger people speak at the conferences, which is reassuring. What's your advice for young people entering the electronic assembly industry? I know that you're not specifically or exclusively electronic assembly, but the industry is a large space. What would your advice be to young people entering or wanting or considering entering this space? What advice would you give them in terms of their education and experience?
Reliability engineering or the
anything
industry.
You want. The sky's the limit.
Well, it's I don't know, I'm not the guy to give advices, especially to the younger generation, because they seem like they know
everything, right? Right.
Yeah, they know everything. But again, I can speak for my field, and what I noticed a trend, and I think this is related to what you were talking about, is that I'd say 15, 20 years ago, I would be working with our customers. And when I say customers, I'm talking about Toyotas and GM and Ford and BMW. And sometimes we have kind of issues like just some disagreements, like, okay, we need to test this unit like this, or here's the test duration. And at that time, I could always find my counterpart, somebody like their reliability expert, and somebody I need to talk to, like same language, and basically kind of solve the problem or come to some kind of agreement. And I've been noticing that lately this person may not exist. And there's more reliance on standards, kind of industry standards or international standards. And those standards, I mean, they don't always apply. So I would say, if I would suggest something, to kind of not rely on those standard documents and kind of understand things better, because you're trying to, I've been in situations where you explain somebody to a relatively young engineer, kind of show physics and this and that, and they would just kind of look at you and say, okay, I have this document right here. It says you need to do this, this, and this, and basically go and do it. And like I said, those documents, those standards are not universal, and they don't have all the answers. So that's one of my kind of thing, comparing what's been happening like 20 years ago compared to what's going on now.
Interesting. Well, that's one of the motivations for starting this podcast a few years ago, was to create a knowledge vault so that the things that are so tribal, they're not taught in universities, can be learned maybe not so much on the production floor, but maybe along with their production floor tribal education. And that way, through efforts from people like yourself, Andre, who are generously giving their time to share wisdom and experience in particular subject matters, you can help grow the next team of engineers.
Keyword. Grow.
Right?
Yep.
I like that term. So thank you for helping to grow reliability engineers and other technicians and people that are involved in this space or who will be involved in this space. I really appreciate your generosity talking to me for the last hour or so. And your knowledge is impressive, and I really enjoyed our conversation. And Thank you for spending time with me and my audience.
And thank you for having me here. I appreciate that.
That's been my pleasure. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. You can send comments or episode suggestions to Mike at mikeconrad.com. Just remember that's Conrad spelled with a K. Thanks again for listening or watching. Until I see you again, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.